Okay, we start up again. I'll put out a different, slightly different version of this traffic program. I have put in also an animation for the individual cars in the end. So you will get the same graph as the one we had, this one, but also here you now have an animation of the different cars within this road window minus 30 to 30 that we are watching. So this was the initial state, and now you can actually see the cars, how they behave, how they move individually, just within this time window of 25. You can change it yourself if you want, of course. So I'll put out this traffic for you. So now this one, that's the one we had. Yeah. So now we are seeking the solution of this equation here. Oops. Why did he show up? That was not my intention. Go away. There we go. Let's see. Here we are. Solve this one numerically. We know the function u. That is just 1 minus the density. Solve it. First choice, forward time, central space. Which here is, as you should know, is a very bad idea, but let's do it anyway. Forward time, central space. Then we are going to need, what notation did I use here? Yes, I still use k and n. Position k, and now new time level minus same location, old time, by delta t, plus, and then I create a central space scheme for the first order derivative. That should now read something like the density for k plus 1 multiplied with 1 minus rho k plus 1. I just inserted a speed limit of 1 for inside the big U here. Then minus exactly the same, but then in the position k minus 1. And then divided by 2 delta x equals 0, which then the 0 there is order delta t and order delta x squared. It's second order accurate in space. So that is my task. Should be straightforward to program that one. Let's see, I keep some of the code here. I don't need the subplot things, so I remove everything down here. And then we can call that one Burger FTCS. Like that. Say now I'm not worried about the individual cars anymore. I can still use the same continuous function for this initial density, but now I can choose my own discretization within this space window from x mean to x max. So say I want to use 100 points. So then my x here would now be 100. Actually, I think the default for linspace is 100, so you didn't have to write it there, but let's do it anyway, just to be safe. And then row, sort of initial row, would now be this function of this x distribution. So that one we should now be able to plot directly, x versus rho of x. So that one I plot dashed red. Let's see if that one works. So there you have the initial distribution from point 2 to 1 within our space window, minus 30 to 30. And then I want to see how that one behaves as time goes by, according to the recipe. So how should we do that one? Well, first of all, we should limit ourselves a little bit here. Axis from x mean to x max, and then we go all the way from 0, say, to 1.1. We're going to go a little bit above here. And then we write hold on, and then I use the same plot sentence, but now I just use an ordinary line, and I put a handle on it. I give him a name, this plot, because that's the one I'm now going to change as an animation. So just give the plot a name, and then we can change the properties for this graphical object during the simulations. We are going to need a time step, so I have no idea. We know the maximum time should be 25, so that one should be okay. I need a delta x. Well, what's he going to be? Well, that should now be x maximum minus x minimum, and then divided by, actually now, n minus 1. So that should be my number of unknowns, n minus 1. That was delta x. And then we can write a pause, and then we start for time level n equals 1, all the way up to ceiling of maximum time divided by delta t. So there we should have our outer time loop. So that one should be okay. And then we have to do this for the internal spatial positions. Now, in this recipe, I'm addressing k minus 1 and k plus 1. So this inner loop has to then start from 2 and go all the way up to n minus 1. So we have to do something separately for the boundary values, of course, but we can do that afterwards. So, and not comma, column. Okay, let's create a left and a right here. So the right one should now be the row of k plus 1 multiplied with 1 minus the same row k plus 1 then I copy that one and create a left. But now minus 1 and minus 1. There I have the two values here side by side, and I can now write my new row in position k equals, well, here also I have to be careful. I can't update him directly. I have to use a separate storage. So let's create a new row. Equals the old one. And then it should read something like minus delta t multiplied with, and then we have right minus left, and then divided by 2 times delta x. There he should be. I have the initial values here. I should also create a space actually, and that would be more neat. New row equals row. Then they are of the same size. Like that. Having calculated all of them, well, from 2 to n minus 1, I have the new ones. Just update them. Row equals the new row. Like that. Then we have to do something with the boundaries. For number 1, row number 1, well, he should then be equal 0.2. That's the beginning in my function. That's the leftmost value here, 0.2. When x gets too big, then this one is getting close to 0. So I use 0.2 as the left boundary condition. A Dirichlet condition. What about the other side? Row number n. We have to give him his value as well. I have no idea. So we use a Neumann condition there. Row n minus 1. Derivative equal to 0. That one really doesn't matter. He shouldn't influence too much upstream anyway, so I'm not so afraid if we do something wrong here. That should be okay. And then we change the values for my graphical object h, and the x positions, when we plotted it up here, that's okay. I want to just exchange the y values. Y data, they are now going to be row. And then draw now, and that's it. Then everything should be okay. Let's try it. So the initial state, and then he explodes. Of course. First order upwind, central space scheme here. That's not any good way to handle this equation. And also you see you're starting to get some noise here as well. You can try, of course, with smaller delta t. Put in a 0 here. It helps, at least in the beginning, but when it gets too steep, no. Unconditionally unstable. So it really doesn't help. Sort of the initial line here, that's actually quite sensible. So what we should have done now is actually to extrapolate that one until you hit this here. Then you would actually have a quite good solution, but that's cheating. We can't do that. So no, we can't use FTCS. Any questions to this one? That's okay. So what do we do? Oh, yes. First order upwind. Well, for a first order upwind, I would like to have here a velocity in front. I don't have that. I have a velocity inside. Yeah, that we could have done, but here actually I prefer to have it the old-fashioned way. I want to have it, you know, on the form velocity multiplied with derivative of whatever we have inside here. That's the form I want. How can I achieve that one? Well, here you have this flux function, little f there. So we can now rewrite that one a little bit. We have the f, that is rho times u, which then is 1 minus rho. So here's a function of rho, and rho is a function of time and space. So how can we do this one now? The f dx, well, you can write it like this. Df d rho multiplied with d rho dx. Just using the train rule. That must be allowed. Then I should get the x derivative of my unknown function here. So that should be quite okay. And finding this derivative here shouldn't be too hard. What do you have? You have rho minus rho square. Well, so he then should read something like 1 minus 2 times rho multiplied with the rho dx. So you see, it's not just to take the large u and put him outside the derivative. That's not allowed. This one outside. You see, we have a factor of 2 here. So where does he come from? Well, if you don't believe me doing this train rule, you can do it the other way if you want. Take this one and you write it then as rho du dx plus u d rho dx. Insert for u, and you will find, yes, they are exactly the same. Just try it if you don't believe me. So now I have this term written on this form here. So whatever is in front here, that's sort of my transport velocity, my advection velocity. So I have to check with this one, is it positive or negative? That's my recipe for this crude version of my first order upwind scheme. So what will we have? If this velocity 1 minus 2 times density, if he is positive, sort of moving to the left, then my recipe will be forward in time, rho k n plus 1 minus rho k n over delta t plus, and then we will have this one in front, 1 minus 2 times rho k time level n multiplied with, and then comes the ordinary derivative, but discretized as an upwind. So this one now should read something like rho k minus rho k minus 1 over one single delta x. That was if it was positive. If it was negative, okay, then it will be k plus 1 minus k. That's all. Any questions to that one? Okay. So now let's baptize this one Burger Upwind. So the rest of the code would now actually be the same. It's just inside here. You have to do something. So let's call him, what did I call him? I called him actually a df d rho. equals now 1 minus 2 times rho of k. Now him being sort of the velocity deciding is it what direction is upwind. So if this one is positive, the rho is positive, then, well, we can actually use the same notation, can't we? Then the right one will only be k. Like that. Else it will be k plus 1 to the right, and the left one will now only be k. There we have it. If advection velocity is positive, we make a derivative between k and k minus 1. If that one is negative, okay, then we create the derivative between k plus 1 and k. That's all. And mustn't forget, I have a factor 2 here. Well, he shouldn't be there anymore. For a first order upwind, you divide only by one single delta x. So let's try that one. That's the initial state, and then we let go. Yeah, it looks quite stable actually. A little jump here, that was a little strange. I don't know what that is. What's this? Looked very strange. Have I done something bad here? No. Let's try and increase the time level and see what happens. Increase delta t. Ah, we still get it. That was strange. I don't see it. He shouldn't be there. Mm-hmm. 25. Okay, no. Strange, strange, very strange indeed. Stability limit, while we're at it here, let's try it. Delta t of 1, will that one work? Yes, it does. Bigger than 1, then we might get into problems here. No, it still could handle it. We have some limitations, clearly. So we have to be somewhat within a stability range here, obviously. But at least this one much better than the central space scheme, which were unconditionally unstable. So here at least we have a chance to obtain a solution. So now we could use this one and then continuing finding the correct answer to the right part of the figure. Here he has used quite an advanced method. I'm not quite sure which one. So he has achieved something like this, which actually doesn't look too bad. compared to what we had. Let's see, we had this one here. After 25 seconds, but something is not entirely correct. You see the step here, he is located here as -10, but here seems to be -13 or something. So sort of the shock front here, propagating backwards to the left, does not have the correct speed. So the first order scheme, as you know, is not the best one. But at least you get something fairly close to reality. Now, I don't have time to go through all the cosmetics to create these here. So I'll just hand out the code for you. Should be here somewhere, I think. If I recall correctly. Something like this. So you have the same animation as we have here, but then plotting everything now together with in the same form that we had here, using the subplots, the initial state, the final state, and then calculating a contour plot for the, say, the intermediate graph there. So this one is the same, actually without that arrow. I have to look at that one. So this is what we get here using the first order upwind scheme. Now let's compare that one to this one. Yeah. Something like this. So not perfect, no. We have missed the actual position here, and from the contour plot, yes, you can see it actually here. The sort of the shock here is tilted, going a little bit backwards in space as a function of time, but here it's more or less steady. So it's not perfect, but at least, as you can see, it has something to do with the correct answer. So your task in the next exercise will then be a little bit more advanced than the very crude version I have made here. To create the contour plot here, I had to use a little trick. You can see the way he has done it here. This is a contour plot of the density as a function of space and time, and he starts out uniformly. And to create this one initially uniform, here the same distances between all the different contour lines, you actually have to use this initial density function in the code. So that is the explanation for this one, the contour plot with x and time, and then the entire ESO matrix, which then contains all the different density in space then for all times. But then you can specify the number of contour lines and also the different level of each individual contour line, here given by a function. And here then I just use the initial residual function. So that's a neat trick. So you don't have to use, for a contour plot, uniformly spaced contour lines. You could use any values. You can specify any number of contour lines and any different value between them as you like. So that's the reason for this one. But the rest should be rather straightforward, I think. So that was today's task. Any questions to that one? Okay, then I think the exercise should be maybe not out yet, but quite soon. Have we started giving out the exercises earlier already, or yeah? So it's out today, maybe, or tomorrow. So then you see the next exercise. Okay, then we stop here.